Okay, here's an explanation of our Unit 3. So we're talking about structure in matter, meaning bonds between different atoms to form molecules and ionic compounds and whatnot. So, first of all, we have learned a little about moles. And its conversion between grams and moles and that kind of thing. But basically, a mole is 6.02 times 10 to the 23rd of anything. Okay, you could have a mole of donuts, although that would, take up more space than the entire planet. But usually we talk about moles of atoms and molecules. So 6.02 times 10 to the 23rd is called Avogadro's number after a scientist, and that's basically the the number that we can use to convert from grams to number of molecules and to moles of a certain compound or whatever. Okay, so atomic mass versus molecular, or sometimes this is called molar mass as well. Molar mass. Alright, so atomic mass, if we look at oxygen, so 8 and 15.999, I'm just going to round to 16. Okay, so oxygen looks something like this. This is the symbol, okay, representing oxygen. 8 is the atomic number, representing the number of protons, okay? And then 16 is the atomic mass. That means that an atom of oxygen is going to have a total of 16 protons plus neutrons. Sorry, I think the video just paused there. In an atom, we have a nucleus, and then we have the first shell, which would have 2, and then we have the second shell, which can hold up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So, 8. An atom wants a full valence shell, or a full outer shell of valence electrons. Okay? So, what that means is that these, the alkali metals, have an extra electron. They want to give it away. These, the alkaline earth metals, have 2 extra electrons, and they want to give those both away. The halogens over here, because they have 7, they're really close to having 8, so they really want 1 more electron. So they want, and these guys, this group also wants, but not as badly. They still have 2 to get in order to have a full octet, or full 8. So we say that the halogens want an electron more than anything, okay? Whereas these, the alkali metals, want to give away. So they're ready to donate, as are the alkaline earth metals. Okay, so, excuse me, when we talk about this word, electronegativity, this refers to how badly the atom wants an electron. So I'm going to write that down. Electronegativity is how badly an atom wants an electron. So the higher the number, the more the atom wants the electron. And on the next page of this video lesson, I have the electronegativity table. But, in my printed copy, I can't even read. Alright. So if we look at some of these values, lithium, for example, is 0.98. So that's low. Potassium, look at that, only 0.82. Whereas if we look over on the right side, something like oxygen, what does that say, 3.4? Sulfur is 2.58. Bromine, 2.96. And fluorine and chlorine are going to have even higher values. So, what this means is that because these have higher numbers, they want electrons more. Okay, so electronegativity is just a measure of the pull of an atom on an electron. And when we get into bonds, which is, well, that's what we're getting into, we look at the electronegativity of the different atoms to determine what they will bond to. Okay, so let's see if we can work through an example. We have H2O. So we know from experience here on Earth that a hydrogen atom and a hydrogen atom will bond to an oxygen atom. Let's see. What am I doing? There we go. Hydrogen and oxygen. So, looking at your periodic table, you see that oxygen has 6 valence electrons. Okay, it wants 8, but it has 6. So what I'm going to do is I'm going to draw them. Here's oxygen. The electrons tend to form in pairs. So this that I just drew, we call this a Lewis dot structure. Lewis after the scientist, and dot meaning we're using little dots to indicate the electrons. And the electrons, if they can, will sit in pairs. That's just how they do. Hydrogen has 1 valence electron, so a hydrogen atom would just have 1, like this. So we're going to take that information and we're going to try to apply it to how the molecule would actually form. So each hydrogen, and you know what? For clarification, I'm going to make the hydrogens in blue. So hydrogen, hydrogen. This hydrogen has 1 electron. This hydrogen has 1 electron. And the oxygen has 6. Now, the oxygen wants 8. So what it can do is it puts 1 here next to this hydrogen, and 1 here next to this hydrogen, and then has 3, 4, and 5, and 6. So what happens is 2 electrons form a bond. So these 2 together form a bond, and these 2 together form a bond. And what we end up with is we can draw this way. We have oxygen. We have a lone pair of electrons and a lone pair of electrons. And we have a bond forming with the hydrogen atom and a bond forming with the hydrogen atom. So the bond and the bond indicate a pair of electrons, and notice how they're shared. One of the electrons is from the hydrogen, one of them is from the oxygen, yet the oxygen is nice and happy because the oxygen feels like it has 1, 2, 3, 4, 5, 6, 7, 8, which is what it wants. That's a full shell. Okay, and the hydrogen, 2 would be a full inner shell, and the hydrogen has 2 around it, and the hydrogen has 2 around it. So basically, atoms get together and form bonds to make themselves happy, to try to complete their outer shell of valence electrons. This we call Lewis dot structure for an H2O or water molecule. And yeah, well, we'll do some more examples. So over here, NH3, ammonia. We'll talk more about the names of compounds, but for now I'll just mention them. Nitrogen has 5, so just off to the side, I'm going to draw a little nitrogen atom. And where those electrons actually go, it doesn't matter, but do know that there are 5 valence electrons, and they're going to form in pairs if they can. And hydrogen, we know, has 1 valence electron, and it will just sit there. Now, NH3, indicating 1 nitrogen and 3 hydrogens. So we could have a nitrogen, and we could have a hydrogen, and a hydrogen, and a hydrogen. And what nitrogen wants is 8. So if we were to, oh yeah, let me draw the hydrogens in blue, sorry. Blue, blue, blue. So hydrogen has 1, hydrogen has 1, hydrogen has 1. And then for nitrogen, look at this. We put 1 here to form a bond with this hydrogen. We put 1 here to form a bond with this hydrogen. And we put 1 here to form a bond with this hydrogen. Nitrogen has 2 left over because we had 1, 2, 3, 4, 5 valence electrons. So take a look. Each hydrogen wants 2 in its inner shell, which is its only shell. 1, 2 for this hydrogen, 1, 2 for this hydrogen, 1, 2 for this hydrogen. And the nitrogen feels like it has 1, 2, 3, 4, 5, 6, 7, 8. Sharing is caring. Okay. And we would draw that like N with its lone pair of electrons. Lone pair meaning they're just sitting there, they're not actually forming a bond. And then these molecular bonds between the nitrogen and the hydrogen, and notice again, or note that a bond is 2 electrons. Alright, moving on, let's see, what do we have? NaCl. Alright, sodium has 1 valence electron. Sodium, 1 valence electron. And chlorine has 7. 1, 2, 3, 4, 5, 6, and 7. So when they hook up, these two will form a bond, and the sodium is happy. Well, okay, so this is there's a little more to this. Because the electronegativity is so different, the chlorine actually kind of steals this electron. So this, yeah, I'll write this down. The electronegativity for sodium is 0.93, and the electronegativity for chlorine, I can't even read it off my page, and is much higher. So the chlorine basically wants the electron, and so what is going to happen is the sodium is going to donate that electron and become positively charged like this, and the chlorine will have its 7 valence electrons and 1 extra, and will therefore be negatively charged. So we could write it like this: NaCl. We're just about to get into covalent and ionic bonds, and there is a difference between the two. This is actually an ionic bond, but for now, with the Lewis dot structures, know that a bond would be formed using these two as shared, and so the sodium is going to be happy because it has lost its 1 valence electron, and the chlorine has gained 1, and you could draw the bonded compound like this. CaCl2 is going to be similar, where calcium has 2 valence electrons, and each chlorine has 7. 1, 2, 3, 4, 5, 6, 7. Forming a bond, which happens to be ionic. We'll get to that later. And then the other chlorine, 1, 2, 3, 4, 5, 6, 7, forming this bond. And we could then draw it like Ca, Cl, and Cl. Okay, that's it for now. Next lesson, ionic and covalent compounds.